Hopefully you had a chance to look at the review. If you have not had a chance to look at the review, please go ahead and do that yourself first before you watch this video. Otherwise, you won't learn nearly as much. So I'm going to go ahead and work through this review, and I'll pause a little part to let you go ahead and work the next problem. But part one here has A, B, C, D, E, F, G. Go ahead and work the whole first page to the best of your ability, and then go ahead and come back and watch me go over the first page, and then I'll take the next page one step at a time going through this. If you haven't worked through the review sheet yet, that's fine. Go ahead and work page one now, and then come back and watch. So this problem here is asking us a couple of things. One of the most important is that we have two hills of different angles. One is steeper than the other. All right, so case one is a steep hill, and case two is not a steep hill. But in this first little part, it mentions that there's no friction. So it doesn't really matter how steep the hill is in this case, because they both have the exact same height, h, from the top to the bottom. Okay, and as a result, when the ball is rolling along the hill that it started from rest up at the top, it may certainly get to the bottom of one hill faster than the other, but when it gets to the bottom, it can't have more energy than it started with. So the amount of energy they start with is based on their height. And the kind of energy they have is G at the top here. And if we set our 0 point that asks us to do in the first part, zero potential energy, we got to say height equals 0 somewhere, so we know where to measure our h's from. So I'm going to put it down here at the bottom. You don't have to put it at the top, but it's nice to have it 0 either at the bottom or the top. And I like to have it 0 at the bottom so that I have potential energy at the top. And when I get down to the bottom, there's no more potential energy due to gravity because I have 0 height there. So the energy that was stored in the position up above, height equals 0, up at point A, stored in the gravitational field. As it comes down, gravity pulls the balls down the hill and transfers energy to them, and they pick up kinetic energy. They get down here to the bottom. They're going to have some EK. We don't need to have any E dis. Once again, we don't have any friction. So with no friction, there's no need for E dis. So we've done part A, and we have marked our 0 point for potential energy. And as to why we're going to do that, we could just say, so we have 0 EG at the bottom. Convenient to have 0 EG somewhere in the problem. And that is the final height that our balls come down to in the problem. That's a nice place to put it at. So we're going to look here, and we're going to see that the Earth, the ground, and the ball are in the system. By taking in the Earth and the ball, we're going to get EG. The ball itself is going to carry the EK in its inertia. And the ground is not important because there is no E dis in this case. So we're going to draw our 3 pie charts for 3 different points, A, B, and C. And we kind of want to begin with the end in mind. It's all EG in the beginning, and then when it gets down to the bottom, it's going to be EK. Right, so at point A, I'm going to draw these 2 things, and it says it's at rest. That word rest was really important in the beginning, because rest means I have no EK right here. So as I'm kind of working through this part of the problem, I want to mention that there is no EK. You don't have to write this on your review sheet, but I just want to be explicit. You do not have EK because it was at rest in part A. However, at point B, there is no EG. Okay, there is no EG at point B or C because we have no height at point B or C based on how we defined our reference point back in that first part of the problem. So If all the energy was stored in EG and it's no longer any of it EG, it has to be somewhere else. There was no friction that dissipated out of our system. So all of it is EK. At C, it's the exact same answer because there's no friction to dissipate it. There's nowhere else for the energy to go. Think about other kinds of energy. There's no springs or rubber bands here for potential energy elastic. There's no chemical energy going on because there's no one's muscles moving. There's no gas in the tank burning. So none of those kinds of energy would apply in this case. And so those are the only types of energy we're going to have is EG and EK. And that's the entire answer for part B. It's pretty straightforward once you understand the storage moves from just potential to kinetic and nothing else. Now it asks us some specific questions about case one here. Is it traveling faster at B or C? And the answer is it's going to have the same speed. Why will it have the same speed? Because all the energy is EK at B, all the energy is EK, energy of motion at C. And so it's going to have the exact same motion because all the energy is motion. I should distinguish here that these pi's should be the exact same size. They don't even look the same size, do they? So we should make sure that we're saying that all the mechanical energy is being conserved. So maybe I should, instead of doing that, maybe I should grab some pi's like this. Some nice little pie pieces. And see here. Copy paste. That's good enough. Yeah. And so if I just select this, let's just copy it, paste it a few more times. That will enable us to have pi's of the exact same size. Each one of these a little bigger than I wanted them to be. That's okay. On the edge of that one. Now they're a little more of the same size. The pi's should be the same size because it's the same amount of energy. So I'm just going to write here next to this that we have the same speed because it's all EK. Will the ball be traveling faster at point B, case one or case two? The answer again is the same speed. As we said, all the energy has the same EG in the beginning because they have the same height. Same EG in maybe at point A. Okay. In that case, is the same EK at points B and C. So we have the same speed at B and C in case one and case two. They're all the same number of units of energy. Units of energy are actually measured in joules, which I don't think we mentioned much in class, but that's the units we use to measure it in. Like we use seconds for time. We use often meters for distance, joules for energy. Not spelled quite the same as a diamond or sapphire ruby kind of jewel. It's actually named after a person known as Joule. So for E, now assume friction acts. Okay, this is a really important change. If you think to yourself, what kind of energy storage effects with friction? Okay, the answer is that we're now going to have some E disk going on in the system. And so when I look at the three pie charts and I think about friction, could friction have more effect in case one or in case two? So case 1 has a very steep hill. Case 2 has a not very steep hill. Okay. So the answer to this question as to where you're going to have more effective friction is that you're going to have more friction effect here. There's two reasons why you're going to have more friction effect. One is that the hill's not as steep, so the ball's leaning more on the hill. It creates more friction. The other reason you have more friction effect is because case 2, the hill is longer, so there's more time for friction to have an impact and transfer more energy. I'm not going to put numbers on how much we're transferring. These are pie charts. Ground is still in my system, and so I'm going to take a look and not worry about energy leaving my system or entering my system, because it's still going to be in the ground of the ball. So let's go ahead and draw our pie charts, and we'll try and draw them all the same size again and make them more realistically small than they were last time. Okay, let's see if we can actually grab these without pinning them all over. We'll put that out again. It's kind of frustrating. I shouldn't have stacked all those on top of each other, huh? Just slip one to place at a time. Figure out where the heck to grab this thing and actually move it and not resize it over and over and over. Guess that works. That thing is frustrating. Yeah, switch the circles here. We're going to pretend they're the same size for the conversation for the moment. And we once again start with nothing but EG. All right, it's all EG because we're at the top and we have height up here at the top, but we have no motion. So up here at point A, it is all height, it's all EG, and they are again at rest. There's no EK, there's no EDIS. Let's start moving it. At point B, we've come down the hill. And let's remember what we said about case 1 and case 2. Case 1 is going to have less friction. We're going to have less EDIS as we go from A to B. And we're going to have less EDIS when we go from A to B. On the case 1, but more on case 2. And I also want to kind of point out here, when you go from B to C on this one, that's not what I highlight. We go from B to C on this case here. It's the same distance as from B to C on this case here. And so we should have the same amount of EDIS produced between B and C in each case. We will not have the same amount of EDIS produced between B and C case 1 and case 2. Let it be there. So I'm going to say there's no EG left. And for case 1, there is just a little bit of EDIS. So we're going to put in some EG there. Forgive me. We're going to put in some EK here. Going pretty fast at the bottom of that hill. Okay, and we get over here, and I'm going to add about 1/4 of the pie. Is EDIS by the end. Not for any particular reason I made it 1/4. I just wanted to. Down here, we're going to have let's go much less. Like this. There's more friction again in case 2, so we have less motion, less energy stored in the inertia, more stored in the heat in the surface and the ball itself. We're going to add about 1/4 to it. I would slow down even more. So for case 2, it is going to be substantially slower. Then we're going to fill in our E dis, sometimes called E internal in some of the worksheets we used. And it is that thermal energy that we cannot recover back into mechanical energy. All right, so just to kind of highlight here that we do have more E dis. I can't read it anymore. We do have more E dis in case 2 than we do in case 1 at both point B and point C. But we did add the same amount of E dis between B and C. Okay, so here we added around 25% E dis in both cases because they're both flat ground, they're both at the same distance, so friction dissipates approximately the same amount of energy into heat. Okay. A couple more questions here at the very bottom. So now with friction, in case 1, is the ball traveling faster at point B or C? And the answer is pretty clear that it is traveling faster at B. And as to why, you can say something simple like friction slows it. Okay, as it moves to C. So friction is changing the energy storage from kinetic energy of motion stored in the inertia of the object to heat energy stored in the ground of the ball. And will it be traveling faster at point B in case 1 or case 2? And the answer is case 1, and we stated why. Okay, case 1 because it has less effective friction because the steep hill has the ball pushing on it less, and it also has less time in which the friction acts because it's going to get there faster. I'm running out a little space here and going to the next page. Okay. All right, let's go on to the next page. If you have not done page 2 yet, please go ahead and pause the video here and go through this page yourself, or this problem number 2. Okay, and then we can do problem number 3 after that together. But do problem number 2, figure out how these graphs match in. Please note that the graphs tell you very explicitly that EG is lighter. Okay, so this stuff here is the EG, and that EK is darker. All right. I hope you got a chance to do that. We can just point out very quickly here that the most height is at 0.5 compared to the bottom of the hill, where I will draw my reference point for H equals 0. It's convenient place for the reference point. So I will call that like H1 because it's the highest height. I'll call this H2 because it looks like it's the second highest height, higher than 0.2 mark, this hill right here. I'll call this H3. It looks like the third highest point of the 5. I'll call this H4. Like this. Okay. It looks like number 1 is my lowest point. Also looks like maybe I should not have drawn my H equals 0 at 0.1 because none of my 5 pie charts have any point where there is no potential energy due to gravity at all. So let me actually kind of erase that out of here and redraw that. And I'm going to redraw it down here. Let me say very explicitly why that is. The pie chart with the least potential energy due to gravity stored in the height is this one right here, letter D. And so even at this point number 1, there must be some H because there's some EG. So letter D as in dog is going to correspond to point 1, where you have the lowest height, therefore the least potential energy due to gravity, stored up in that height or the gravitational field between the Earth and the ball there. The one with the next smallest portion of EG looks like C. Right? And so I would say this one's going to go with number 3. And the one with the next least of all, the middle one, right? This light colored EG is right here. So it looks like 0.2 has climbed quite high right there. The ball's changed its speed. It has slowed down. So this is B. All right. And just to state obviously what the other kind of energy is here. And we can say at this point whether or not it's frictionless, just to look at it. I would say it is frictionless. And I'm saying this based on the fact that there's only 2 kinds of energy. If it was not frictionless, we would need EDIS, or we would have energy leaving the system. And our pies are getting smaller and smaller. And one of those would be happening. So this must be the EK down here because it's the dark. Right? This darker shading is EK. That's moving very, very, very fast. And that's also why I put it at D, because at the bottom of the hill, it's moving very, very, very fast. And it'll be moving slowest at the other extreme, all the way up here at the top at 5. Okay, so that will be letter E as an elephant, because it's moving very, very, very slow up here, because the energy is stored in the potential of the EG. That's this big slice. Right, and lastly, of course, letter A is going to go right here at the second highest height, where it's almost all EG. It's almost all the way to the top of the hill, but not quite. It's number 2. So one harder thing on number 2 was that the H equals 0 had to be below all the points. That was an interesting little twist in the problem. And you did have to state or underline or do something about frictionless. I said out loud how you can tell. You can write it down yourself. But you can tell that because there's only 2 different kinds of energy storage in the pi, potential and kinetic. There's no dis. Pies aren't getting smaller, so we don't have any energy leaving our system. So there's just only 2 kinds of energy that are available. Go ahead and read number 3 to yourself. You haven't done it yet. It's got parts A, B, C, D, E, F. We'll go ahead and go over it. Let's go ahead and go over this. And so it gives us 3 points to look at. Point A right here is when it is first, just before it's released. If it's not released yet, it has no motion whatsoever. You drop the clay ball. And we should look at our schema here before we even dive in that far. So let me kind of draw out some schema. And we're going to put everything in our system. All right, so I want to put in clay. I want to put in the floor. It's going to drop onto. We'll have some heat dissipated. We're going to put in the earth. That'll allow us to have gravitation potential energy in the system. Those are our 3 objects. And I see that the earth is going to transfer energy to my clay by making it fall, because earth causes gravity. So the energy stored in the gravitational field is going to transfer to the clay and become kinetic energy. The clay hits the ground. Some of its energy transfers in the heat of the clay as it changes shape and deforms. And some of it is going to transfer to the floor. Okay? So that's kind of the schema lines there pointing where the energy transfers within the system. We often will draw little circles around the actual objects in the system. I'm just running out of room here a little bit. I drew it. And let's go ahead and look at our first energy pie chart, where it's all EG, all the energy stored in the gravitational field. Again, if it is, if we say before it's released at point A, then it's not moving yet. Okay, so there's no kinetic, no dis. Point B, I'm also going to say that we don't have any dis because there's no air resistance. Okay, point B is just before it hits the floor. And so we'll go ahead and drop our little pie chart there. And right before it hits the floor, it is either all EK, or you could have a smidge of this energy still being EG. I'll go ahead and put it all EK. I'm going to assume it's only about a fraction of a millimeter above the floor, and so height's approximately 0, so EG is approximately 0. And in a test, if you had a tiny sliver of EG, that could be acceptable, but we're going to kind of take that to an extreme where it's just about to hit the floor and there really just is no more EG. These circles should have been drawn the same size. This last one is a little bit too big. That's all right. Just change the size a little bit. And so once it hits and goes splat, okay, point C is after it hits the floor, there's no more EG because we have no height above the floor. That's where I'm going to put my gravitational potential energy equal to 0, the reference point right at the floor. There's also no EK because it's not moving once it stops at the floor. So there is nothing but E dis. It's all heat. E dis or E internal, depending on the label. Okay. Now repeat the process with only the lump of clay in the system. So to think about that, if there's just clay in our system and the earth and the floor are outside of our system, then what kinds of energy are we allowed to stick in here? So here's only one object, right? And that is our clay. And so as it begins to fall, okay, we're going to have the earth, okay, and that's going to transfer energy to the clay into our system as it falls, and it'll move faster and faster toward the ground and store energy in its inertia. It's going to hit the floor. When it hits the floor, and a great deal, but not all of the energy leaves the system and becomes E dis. So this is kind of a weird little thing. I would say for A, you get no pi at all. You get no pi because all the energy is stored in the gravitational field between the Earth and the ball. So without the Earth in the system, you just can't have a pi with EG. And then we'll get to the next step here in part B when it's almost at the floor. And for this part, I would say we're going to have all EK, just like before. And then when it hits the ground, we would have a little bit of energy still inside of our pi because it is heated up some as it went splat on the floor. But it's a much smaller pi now deliberately because most of the energy or a lot of the energy is transferred to the floor. Okay, that's a pretty hard question right there on letter B. And so we're not going to do a whole lot of stuff about changing pie chart size on the test. We're not really going to do that really at all on the test because I don't want to grade your really big and really small pie charts and trying to decide which ones are bigger or smaller. So we don't do a whole lot of that there. We do shift things in and out of systems for bar charts that we did in class. And we are not going to do it for the pie chart. So is energy conserved in the system used in part A? How do you know? It is conserved in part A. So in part A, we have 3 pies that are the same size. And so we have it transforming from one form to another, but it didn't leave our system. Is energy conserved in the system? The key here being in the system in part B. How do you know? Okay, so this one was yes. Right. So all pies same size. All energy stayed in system. If I jump to the next question there, let's change colors. I'll say no, okay, because the pi it changed size. And we had energy transferred in and out. Transferred in from the earth, transferred out to the floor. So how can energy be conserved in some cases and not in others? Well, it's conserved in all cases, but it's not conserved inside the system in all cases. Okay? And so I'm not going to write all that out. So in all cases, we didn't create energy or destroy energy, but if it transferred out of our system, And the way the question's worded with this word in, it would say in the system. If our system includes the whole universe, that's not a problem. Energy is always conserved. It didn't escape the universe. If we let our universe go out to the outer bounds of all the stuff, whatever that would be, if such a point even exists, we haven't found it yet with our telescopes, but perhaps it exists. As the clay hits the floor, more energy is dissipated in the floor or in the clay. How do you know? And I'm not sure how you know whether there's more in the clay or the floor, other than the fact that the clay had a great deal of change of shape. Okay, so the clay had a lot of movement of its parts as it smears out and flattens out. So the clay might have quite a bit of heat inside of it. But again, you could look at the pie chart size. And that would help indicate what the person was trying to communicate. Okay. Let's go on to number 4. Just check the time here. Okay. If you haven't done number 4, please go ahead and work on it yourself. Go back and we will look at it. Looks like number 4 goes way down to part D there. And we're getting into bar charts now. So finish up 4 and come back and unpause and we'll begin. Alrighty, and so let's go ahead and start off. We're going to make just a couple notes here as we read. Everything's in the system. So we don't have to worry about energy leaving our system or entering our system. We have the earth and Tarzan, the vine and the ground and everything. It reaches the highest point on the right-hand side. So almost like a swing set. Tarzan is going to swing out and come to a stop. How high will he be? Well, we're going to assume that there is no air resistance. Right? That means there's no E-dis. So all of our energy is mechanical. Again, mechanical are the two types called kinetic and potential. And so we're transferring from whatever Eg is stored in the beginning in the height above ground. That is becoming kinetic as he moves downward, and gravity causes him to go faster and faster and faster, taking out of the storage of Eg and adding it into Ek. And that's all going to transfer back into Eg again. Okay, so at some point over here on the right, he's going to reach the same height. Now, if he was running high speed and leaped onto the vine, he might have some kinetic energy already. He could swing up to a higher location on this right-hand side. But it says that he is standing, and so that's not how I'm reading the problem. I'm reading the problem that's more like a swing set. Someone pulls you back, holds you perfectly still, and lets you go. If there was no friction or air resistance, you go up to the exact same height. So when he reaches the right-hand side, I will label point C right here, right? And even like the flat line going right across to it like that. Okay, and say that's where point C is. Sketch the zero potential energy line and say, why did you choose this position? And let me see if Tarzan actually makes it part B. Did he land at part B? I don't see that. So there's not one answer for where you're going to put zero height. You can put it at the ground. I often put it at the ground. If we do put it at the ground, just to clarify, there's going to be some height, right here. So there's some height there, but there's more height right here, and there's more height right here. So we're going to have some Eg in the middle, but we're going to have more Eg on the sides. We're going to have no Eg at point A or point C. We're going to have some Eg at point B, right? So I have done part A, I've done part B. Now on the axis below, let's plot the Eg as a function of going back and forth, back and forth. I just drew these little green bars to show you the height, where the height is related to Eg. So I have a lot of Eg at A, a lot of Eg at C, not too much at B, but nor is it zero. And so I would kind of draw, and I'll make it the same color as my little highlighter stuff I had before. this. Right. And where I chose to draw my maximum and my minimum was arbitrary because there's no units over here. Okay. Then I want to plot a dotted line of EK. I'll also just shift colors to make it a little simpler to see. The EK actually starts at 0, okay, and it's going to reach a maximum at B and then go back to 0. Now, how high should this maximum be? It doesn't matter because there's no units, there's no numbers. So it's kind of up to me as to how I want to draw it. I just drew them so they wouldn't actually overlap. It did say use a dotted line. I didn't do that. I apologize. So we'll just keep moving here, though. How would your graph change if air resistance did act? I'm going to say they would vary less from top to bottom with time. And what I'm saying with that is that they wouldn't go up and down as much as time went on. Let me kind of just show what those would do. For kinetic, you might have it just not go as high up every time. And for the potential, it might not come back to the same height every time. It would have the same amount of energy at point B, so it'd still go just as low, but it would go a little bit less high every time. We call that kind of like a damped motion, like something's damping out, pushing down or making it go away. Let's go on to number 5. If you haven't done number 5, please go ahead and read it and do these little charts down here at the bottom, and we'll go over number 5. Okay, student lifts up this box, draw a schema to indicate the system, dashed line, and complete the bar charts below. Okay, so here is my schema, and we do have box and earth in the system. We also have a ground here. It doesn't look like you're in the system, right? The person, he or she is not in the system. And so let's go ahead and decide how the energy is transferring. So with our box and the earth in the system, we can write those objects, box, earth, ground. I think the ground's going to have really any influence in this problem. So here's my box, here's the earth, here's the ground. And energy is flowing into my system, flowing into the earth by someone lifting up the box, okay? So the person who is lifting up the box, I'm going to put the student out here. So their chemical potential energy of their muscles is becoming gravitational potential energy as they lift it up and they hold it there. It's not moving, not shaking it around. And so they're going to lift it up there when it gets up to point B. I'm sure in between A and B it had kinetic. It doesn't have kinetic at A, it's sitting still. It doesn't have kinetic at B, it's sitting still. Okay, so in the beginning, I will not even list chemical energy because the person is not in the system. The student is outside the system over here, right? And then we're going to have energy flow into the system. And let me see, for EG, I'm going to decide it has 4 units. Yes. No particular reason. I just wanted to pick 4. So I'm going to divide this up. I get 1, 2, 3, 4 little boxes. Okay, and this is going to go from the student right into the earth in my system. I also have the box. Now, so there is energy entering my system from the student, and that is the bar chart for this one here. All right. Moving on to number 6. Go ahead and work on number 6. Number 6 is our last problem, and it's got a whole bunch of parts, a whole bunch of bar charts and stuff. Let's take a minute and work on that, and then we'll go on. All right, let's take a look here. This one has some interesting, weird, complex things that I'm going to say are almost open to interpretation here. So it says that by point B, that's right here, it says at point B, the spring is completely stretched. The cart is no longer touching it. If the cart's no longer touching it by B, the cart's not going to have any more energy added to it. And it says, though it continues to vibrate. Now, if the spring is still vibrating back and forth, bouncing in and out, in and out, in and out, it still has some energy in it. And that's weird. So even after a cart leaves the spring, we're going to have some elastic energy in the system as that spring vibrates and goes back and forth. Could be kinetic at some points, could be more potential at some points as it goes back and forth. Should be some elastic potential energy back there. I'm going to choose to imagine. Okay, A, B, C, D. So first off, I'm going to draw a zero line. I'm going to choose right here, which makes sense to put at the bottom. That means I'm going to have EG equal to 0 at the bottom. Okay, I have no height there. I'm going to have the most EG up at letter D. And it says the cart just makes it to D. I'm going to interpret that cart just makes it to D. It gets up to D and it stops. I'm going to say at D I have no EK. I'm making some notes here for the problem. So there's no EK at D because it just makes it up the hill and stops. So now when I get down to the bottom, I can remember these things when I'm filling in my bar charts. So as I look at the problem here, it does tell me to assume that I do have air resistance and I do have friction. Let's draw our schema for our situation. This is a little bit complicated. I assume everything's in the system. I'll make a nice larger dotted line area for my system. And I'm going to jot down things that are in my system. I have a cart. I have a spring. I'm going to have the earth. I'm going to have ground. Okay. This is a pretty complicated system because the energy is going back and forth between different objects. So as I kind of track this, I'm just going to color code it. That's the first energy transfer. Spring transfers energy to the cart. So it was elastic potential in the beginning. It's going to become kinetic. And then it gets a little more complicated. So the cart is going to go downhill. As it goes downhill, the earth is going to transfer some energy to the cart because it was gravitational potential. Then it becomes more kinetic. At the same time that's happening, you also have some energy being transferred to EDIS with the ground, right, as it's going down that first hill. And then we're going to have all the crazy weirdness of the cart is going to give a whole bunch of energy back to the earth. Not all of it, but most of it as it goes up to D at the very top. It's also going to keep on giving a little bit to the ground. And that energy can be dissipated out of the system. Forgive me, out of the system, it's going to be dissipated into heat, so it's no longer used as mechanical energy, that is kinetic or potential. So let me sketch the bar graphs showing how the energy might be stored. Right, so at point A, we said we have elastic. How many units of elastic? I'm just going to make it up. 1, 2, 3, 4, 5, 6, 7. There's 7 units of elastic. And there's no other kinds of energy as far as kinetic goes or disk yet. We do have some height here. Okay, so with some height, we're going to have some EG. I'm not sure how much. I might just choose like 2 or 3 units of EG. Okay, then we come over here to the next part. The next part, remember I said I'm going to interpret that there's some energy left. There's going to be one energy there. Okay, at the bottom there'll be 0 EG because I'll put 0 for all these. All right, there's going to be 0 EG because there's no height at the bottom. There'll be lots of EK. Let me figure out how much EDIS there is. I'm going to say that there is 1 unit of EDIS and 0 chemical. So I do the math here, okay, and I add up all the different types of energy here. I can get like a little math, 7 plus 2. So units of energy is 9. And I just counted up the bars again to get. Well, I want to have 9 here also because energy is being conserved. Everything's in the system. I only have 2 right now, and that tells me exactly how far to put my EK bar. It's also going to have to go up 7. Is there a right answer for the way I did that? That they're 1, 7, and 1? No, there's not. You could have chosen 2 and 3 and 2 if you wanted to, or some other combination of numbers, as long as it was kind of believable. I'm going to keep on putting my 9s over here. They better all add up to 9. I just did that wrong. I apologize because B is still high up here. So let's get rid of some of that kinetic. Let me add in some gravitational potential. I had 2 over there. I'll put 2 back here. I'm the same height. So this should only go to 5. Right, and my 2 went up 3 by accident. Erase that and make it 2 appropriately. There we go. So we still have 9. 1 and 2 is 3. 5 more is 8. 1 more is 9. Again, I had to add back in some EG because point B is up here at the same height as A. I have the same EG. Okay, now here I really do have 0 at the bottom. I'm going to leave this 1 as it vibrates. I'm going to have a little bit more EDIS. Okay, we'll have 2. No EChem. Looks like I need 6 more units now. Okay, I have to add up to 9. So 1, 6, and 2 is 9. Coming to the last stretch up here at D. Up here at D, let's remember we said EK is 0, and there's a lot of EG. Obviously some EDIS. So I'm going to leave my 1 in E elastic because it's still vibrating. I'm going to say 0 for chemical, 0 for kinetic, and we're going to say it has a whopping 4 of EDIS up top. I want to add up to 9. I'm going to say up here it has 4. Okay, so those numbers were some I just chose. It don't have to be that way, but that's how I divvied up the energy as long as I understand what I'm doing. Good. Now assume only the cart is in the system. If the energy in your system changes in points, where the energy was transferred from and to. So let's take a look. If only the cart's in the system in our schema, it is going to receive energy here in the beginning. Oops. And then it's going to dish. It's also going to receive some energy when it goes from B to C. And then it's going to dish out energy. It's not going to dish out some of its energy. It's going to dish out all of its energy. The only energy the cart can have, if the cart's the only thing in the system, is kinetic. In the end, it will lose all of its kinetic. Okay? So in the end, it will have no energy at all. It'll be 0, 0, 0, 0, 0, because there's no kinetic and the cart's gone. At A, it'll be all zeros because the cart's not moving, and only kinetic energy can be recorded if we're putting in the cart. I'm going to amend that statement. You could have a little bit of EDIS in the cart and in the wheels, right, and a little bit in the ground. So let me edit that and say you could have some EDIS here. And we can make it 2. Let's make it 2. So we can have less EDIS somewhere else in the system. Not have much of a fractional thing going on. Down here at C, we'll put 1 EDIS. Okay. And we will put maximum EK. See how much EK there was before. I said 6. Keep it the same. Great. No chemical, can't have EG without the earth, can't have E elastic without a spring, and there's no spring in the system. Spring's still vibrating, but it's not in our system. And now let's come back to point B. It has just been pushed off of the spring, but has not gone downhill. Did 5 before. Play the same. I'm going to say just a fraction of EDIS here, all right? And these are all still 0. Now it asked us also to note, right? Note where the energy was transferred from and to. Okay, so we can make some notes here. I would say from spring, let's say from Earth, and not really, and some of it is also to the ground. Oops. We're getting some dis. Okay, as energy is flowing in from gravity, some of it's becoming kinetic, some of it's going to the ground. And then at the very end, we're getting to the Earth, which goes up the hill, and to the ground. Okay. And so that is the review. And hopefully you will have a chance to have all the right answers here and kind of look them over between now and your test on Thursday. Best of luck to you. Please feel free to chat with a classmate and have something explained in a different voice if you don't understand it. And hopefully working on this review in class and listening to this 51-minute video will have taken most of the class period. And I will see you when I get back. Have an awesome week.